Hey there, everybody. Well, you've made it. It's time for the last topic in our course in Math and Logic, and I'm happy to say it's kind of a cool one. We're going to combine some logic ideas that we've built now and look at what are called logic circuits, which are a visual way to represent Boolean logic expressions. And that's going to allow us to see the logic behind how a processor actually performs addition. And that'll be where we have to end the class. So there's kind of a neat animation on your screen that might not make much sense right now, but it will at the end of the lesson. So we're going to come back to that animation in a little bit. Let's get started. So the first thing we need to do is we need to establish what logic gates are. Logic gates are part of a bigger thing called a logic circuit. And a logic circuit is basically just a decision-making network, and it produces outputs based on binary inputs. That's a lot like a Boolean table that we've done where each row is a certain condition of the inputs. So that circuit on your screen has got a bunch of symbols in there that are all giving an indicator of what should happen logically, and that's what we're going to look at. But let's break it down into its individual pieces. First of all, an AND gate. An AND gate is a logical gate that will produce an output based on two inputs. So the AND gate does just what you would think the logical operator AND does. It'll produce an output of 1 if both A and B are 1. That is to say, it represents the Boolean operator of multiplication. The thing to notice here is that it looks like exactly half of an ellipse with a flat edge on the left side. Now as our animation scrolls through, I want you to notice that there's 4 possible inputs here. We can have A equal to 1 and B equal to 0, or B equal to 1 and A equal to 0, or both 0, or both 1. But the only thing that triggers our output Q to be 1 is when A and B are both 1. Otherwise, the output is 0. So with that, let's determine the output of the following pairs of bytes of data, the top byte and our bottom byte, if they are fed to an AND gate. So we're basically saying we're going to feed these 2 bytes or strings of 8 bits of data into an AND gate, and we need to figure out what the output will be. So we look at these pairwise. We'll work our way from left to right. When a 1 and a 0 is fed into our AND gate, the output is a 0. When a 1 and a 1 are fed to our AND gate, the output is a 1. 0 and 0 yields an output of 0. 1 and 1 yields an output of 1. 1 and 0 yields an output of 0. 0 and 1 is 0. 0 and 0 is 0. And 1 and 1 is 1. So if that byte and this byte are fed through an AND gate, this will be the output byte of that AND gate. And all of a sudden, you should start to kind of feel like this is getting a little bit mathematical, because these are 1s and 0s, and the AND gate is making this decision, but these can also represent numbers. We're feeding 2 numbers in, we're getting a number out. Now it's not adding them, it's not quite that simple, but it's starting to have that feel about it, right? The second kind of gate that we're going to work with is, as you would guess, the OR gate, which is for our other Boolean operator of addition. The OR gate produces an output of 1 when the input of A is 1, or if it gets an input on B of 1. That is to say, it produces a 1 if A or B is 1. Now, notice that the shape is very similar. The only difference is the edge of that gate has a curve on it instead of a straight line, and that is the thing that distinguishes an OR gate from an AND gate. So again, as the animation here rolls through the different combinations, you'll notice we can have 0, 0, A is 1, B is 0, A is 0, B is 1, or A and B are both 1. And you'll notice that our output Q is 1 either time A or B provides a 1. The only time the output is 0 is when A and B are both 0, or in other words, when neither A or B provides a 1. So let's feed these exact same 2 bytes of data through an OR gate. Okay, so the OR gate is represented by a curve on its left side here. We're going to get an output of 1 for every pair of bits that give us either a 1 on one input or on the other. So our first pair, we have 1 and a 0, that's a 1. Second inputs, we have 1 and 1, that'll be a 1. 0 and 0 there, we have no 1 input, and so we have a 0. Here we have 1 and 1, that's a 1. 1 and 0, well, that gives us a 1. 0 and 1, there we have a 1. There's 0 and 0. We need a 1 here or here, and we don't have one, so that's a 0. And our last bit is also a 1. So there's our 8 output bits. Notice that they're not the same as they were for an AND gate, which is pretty much what you'd expect. The third type of gate is called a NOT gate. The NOT gate simply produces an output that is opposite of its input. In other words, it is the negation. So our three main Boolean operators, AND, OR, and NOT, all have a logic gate that perform the exact same function. And the NOT gate is often called an inverter. And as you can see here, the NOT gate is basically a little triangle that shows the direction of flow with a little circle on it. And that's the universal symbol. And of course, you'll notice that there's only one input on a NOT gate. Whatever that binary input is gets reversed. So let's jump right in here and draw a logic circuit. Let's draw a logic circuit for the negation of A or B. Well, this is really a question of order of operations. That negation line up above A or B depends on what the output of A or B is. So we would start with an OR gate with, of course, two inputs, A and B, and that's going to produce some output. Now, what we have right here, this would represent A or B, but we want the negation of that, and so we should take that output and reverse it with the NOT gate or with a negation symbol. And by putting that negation on there, now we're reversing the outcome of A or B, and we've drawn our logic circuit. And that's all there is to it. I'd like you to try this one. I would like you to draw a logic circuit for the negation of A times the negation of B. Pause the video, go ahead and do that, and then we'll take a look at your result. Okay, well, be careful, because here's a common mistake I see. I often see people say, oh, okay, I'm going to start with not A and not B, and I'm going to run those into an AND gate. But that's not right, because our inputs can't be negation values. Instead, what we have to do is we have to start out with inputs A and B, just like we did up above. We're going to have an input A and we're going to have an input B. Now, if we want the negation of those, we have to draw that inverter or that NOT gate in order to switch those over. So we have the negation of A and the negation of B. Now, after they've been negated, those two can be fed into an AND gate that represents multiplication. And there's the circuit that represents the negation of A right there and the negation of B right there, joined by that AND gate. Now, are these circuits equivalent? Well, let's do a little testing here. Let's pick a couple of inputs and see what our outputs are. Suppose we let A be 1 and B be 1. The output here would be A or B. The output here would be a 1. And that would be negated, so our output would be 0. What happens if we run it through this gate? If we let A be 1 and B be 1, those both get negated before they're fed into an AND gate, and we have 0 and 0. The output there is going to be 0. We got the same output. Let's check one more. Let's let A be 1, but let's let B be 0. If we feed those two inputs into an OR gate, we still get an output of 1, and that'll be negated to become 0 up here. So 1 and 0 would still yield an output of 0. On our AND gate, if we let A be 1 and B be 0, the same two inputs, the A gets negated to become 0, the B would get negated and now become a 1. And if a 0 and 1 are fed into an AND gate, we would need them both to be 1, but they're not, so our output is 0. We still have an output of 0. And in fact, if you check A equals 0, B equals 1 in both of these, and 0, 0 in both of these, you're going to find that the outputs match every time. These two are equivalent. From a logic standpoint, that circuit and that circuit will do the exact same thing. So which one is better? This one only has two gates, an OR gate and an inverter, whereas this one has three, two inverters and an AND gate. So that would be considered the simpler circuit. And it should make sense that they're equivalent because De Morgan's property says we can break the line and change the sign from our original expression and it will yield our new one. Let's do another one. Let's draw a logic circuit for the Boolean expression shown B times A plus the negation of B. Well, here again, we're going to start with our parentheses work. And parentheses say that we need to start with Boolean addition, that is to say, an OR gate. So let's start right there by drawing our OR gate. Now the inputs of our OR gate are A and the negation of B. So if B is going to be one of our inputs, we have to run that through an inverter before it goes into our OR gate. So the work in parentheses here, A or the negation of B, we're done with that. That's A or the negation of B in our OR gate. But that gets multiplied by B, or in other words, we can have B and the output of this. And so this is going to run into a larger AND gate where the outcome of our parentheses goes into that AND gate, or B can go into that AND gate. Now we don't want to make another B over here. We already have one input B. So we're just going to tap off of that and let that be the input into our AND gate. So this AND gate gets triggered by having B and the outcome of A or not B, and we've drawn our logic circuit. Be careful there, because a common error is to think that this B and that B are going to be different B inputs, but each letter should only be represented one time, and we should tap off of it other places where that input is needed. Okay, let's draw a logic circuit for this more advanced Boolean expression. So let's start with our three inputs. We have A input, and we have B input, and we'll have C input. Now let's begin by the negation of A and the negation of B. Those are in parentheses and A, B are next to each other. So we'll start out with an AND gate where our inputs are A negated and B negated. So we're going to have A with an inverter, but we're also going to have the negation of B going in there. So let's do that. We'll negate B and feed that in there. Okay, so we just took care of A naught and B naught. Now we also have A and C naught in an AND gate, and so let's put another AND gate right next to that. And the inputs here are A. Now I don't want a new A. I'm going to tap off the A that we already had before it's inverted. And anytime we want to cross one of the other lines, which you often have to do, put a little jump symbol like that, and it looks like a little bridge that's going right over that, so it's clear that it's going over that and not connected to it. And along with that we'll have C, but we'll put an inverter on C, and that will feed into that gate. So here's our A naught B naught AND gate and our A C naught AND gate. Now those two are combined by Boolean addition, which means we can have one or the other, and that means these are both going to go into an OR gate. There, and at this point I've represented everything inside the parentheses. Now that output is being Boolean added to a BC AND gate, so we'll put that alongside another AND gate whose inputs are B and C. So C we can tap off right there and go into our AND gate, and B will tap off right here, make sure that we go over so it's not combined, and we'll go into our AND gate. There's the output of our parentheses. Here's the B, C AND gate right next to it, and we can have one or the other, and that means that these two feed their own OR gate. So I'll take those two outputs and feed them into another OR gate right there. And there's our Boolean logic circuit. Now I want you to notice something. We have three multiplications here between B and C, A and C naught, and A naught, B naught. And we have three AND gates, one there, and one there. We have two Boolean additions in our expression, one inside the parentheses and one out, and we have two OR gates. We have three inverters, C naught, A naught, and B naught, and we have three inverter symbols. So there's our logic circuit. We're done. But we can ask an important question here, and that is, if we look at that, it looks kind of messy. Could it be simplified? Well, we can go about this a couple of ways. We can apply Boolean algebra, or we can do what you just finished doing. Let's make a Karnaugh map for this and see if it's simplifiable and if we could have made a simpler circuit that does the same thing. So let's make a Karnaugh map. Notice that we have three inputs here, and so we're going to have a Karnaugh map that follows the standard Karnaugh setup for a three input expression here. Notice again that in any two adjacent squares, only one parameter is changing, A naught, B naught to A naught, B to AB to AB naught, and then that wraps around. Now if we go look at our original expression, we had BC. That means that we're going to have ones here and here. We have AC naught, which means we're going to have ones here and here. And we have A naught, B naught, which means we're going to have ones here and here. Zeros everywhere else. Now, what's the best grouping we can do on our Karnaugh map here? We always like to have the biggest groupings possible. There are no groups of 4 that we can do here. The best that we can do are groups of 2. And so we can group those two, and those two. And in fact, those were the originally 3 pairs that we wrote down, and so that matches our original expression. No, this one can't be simplified based on our Karnaugh map. Okay, I'd like you to do this one for practice. Look at the logic circuit that's shown there and see if you can write the Boolean expression that corresponds to the circuit that's shown, and then determine the output when A is 1 and B is 0. Pause the video and unpause to see the solution. Okay, well let's take a look here. So for starters, A and B are fed into an OR gate, and so we know right off the bat that we're going to have A plus B. But the result of that, which means we can bundle that up inside of parentheses, is fed into an AND gate where its output and the negation of B are fed into. So in other words, this is going to be multiplied by, because it's an AND gate, the negation of B. And there it is. That is your Boolean expression. Now let's determine the output when A is 1 and B is 0. Well, if we let A be 1 and B be 0, the output of the OR gate will be 1. That'll get fed to the AND gate, and since B was 0, when it's negated, it'll be a 1. And since the AND gate is being fed a 1 and a 1, its output will be a 1. Okay, here's one more I'd like you to do for practice. This is an important circuit. See if you can write the Boolean expression that corresponds to this circuit shown on your screen. Pause the video, give it a shot at that, and then unpause to see the solution. And then we're going to look at this one a little bit deeper because there's something important going on here. Unpause when you're ready. Okay, well, here we go. Let's start with that first OR gate where A and B are both fed to the OR gate. We know that that is going to be simply A or B. And since there's more going on, since that result goes on to another gate, we'll put parentheses around that. But notice that A and B are also feeding an AND gate. So apparently we're going to have A times B as well. And I could write just AB there, but I'm going to leave the multiplication symbol in. There we've got our AND gate. But look at what happens to that A and B gate. the output gets fed straight into an inverter, and so that means that we should negate that output. And notice that the output of our OR gate and the output of our negated AND gate both get fed to another AND gate at the end, and so these two results should be multiplied. And ultimately, that is the Boolean expression that corresponds to this logic circuit. And you're done. If you got that, great job. But I want to show you one other thing here. Look what happens if we apply De Morgan's property to the right side in our right parentheses here. The left one won't change, but that right one will become the negation of A plus the negation of B. We're going to break the line and change that sign, and that's what we get. So we have A or B and the negation of A or the negation of B. Now there's a certain symmetry to that, right? What this means is, in order to get a positive result here, we have to have either A or B giving us a 1. And, or in other words, we also have to have the negation of A or the negation of B giving us a 1. What that means is either A or B has to be a 1, but it also means either A or B is going to have to be a 0. And what we call this is, this circuit that you see, this is called the exclusive OR gate, or in other words, XOR. And it passes a 1 only if A or B is a 1, but not both. If you were interested in that, you could go back to section 9.3 in your text, and it shows some of these alternative logic operators that we've kind of skipped over because they're not the fundamentals. But that's one of them, the exclusive OR gate, an important logic gate. Okay, here's the last problem I have for you in this section. Write the Boolean expression that corresponds to the logic gate shown. Now, you might look at that and say, ugh, that's a mess. You're right. And our goal is to simplify it. So write the Boolean expression. We'll check and make sure and see if you've got that right. Then we'll simplify it and see how much more simply we could draw this circuit. Unpause to see what the Boolean expression is. Okay, well, let's start at the beginning here. We have an AND gate that's fed by the negation of A and B. So we can start by saying the negation of A times or AND B. And we're going to do more with that, so we'll put it in parentheses. Now that output feeds another AND gate whose other input is C. So we can say not A and B and C. And at this point, what we have covers the shaded region on your logic circuit shown. Now, that result goes into an OR gate, so we can add on to that the other thing that's feeding our OR gate, which is an AND gate that's fed by the negation of C and the same thing we had earlier, the negation of A times B. And at this point, what we have is shown and shaded on your screen. Now, as you can see, we've got one more OR gate, so we can add on another alternative path here. And the OR gate is also fed by another AND gate. And the AND gate is fed by the negation of A and the negation of B. And so that'll do it. There's our entire Boolean expression. And hopefully that's what you came up with. Now let's see if we can simplify this. Let's use Boolean algebra to do this one. If we start with these two terms on the left and the middle terms, they have a common factor of A naught B. So let's factor that out to the front. We're using the distributive property in reverse there, and we get A naught times B times, what will we have left? From there we have a C, and here we have the C naught. And of course we have plus the negation of A, the negation of B at the end. But we know that C or C naught Of course, that's going to always yield a 1 because C will always be either true or its negation will be true, or a 1, you might say. And so that becomes 1. And so we have A naught times B times 1, or A naught B naught. But of course, 1 is the identity, so this really becomes A naught B or A naught B naught. But now we have a common factor of A naught, so let's factor that out, and we're left with B or B naught. But we know that B or B naught is 1, just as it was for C up there. And so we have the negation of A times 1, which is, of course, the negation of A. So believe it or not, this complex circuit really just boils down, and no matter what ones and zeros we feed it, it will ultimately just give us the negation of A. So we could replace that big, messy circuit with just this. B and C have no effect. The output of that circuit depends solely on the input of A, which gets reversed. Okay, well, I won't ask you to do anything more here, but I do want you to see a real important result of this called the half adder circuit. And this is the circuit that performs arithmetic. This is the circuit that performs addition. Let me show you what I mean by that. Let's take a look at a real simple binary addition problem. Let's add 1010 to 1100, and I want to show you how this circuit would actually do that math. Okay? So for starters, you know that if we add 0 plus 0, we should get a 0 in this spot. But let's face it, processors don't know arithmetic. We can just teach it through logic gates. And so this first column, 0 and 0, we're going to let this be the A input, and this will be the B input. So A is 0 and B is 0. We put those into our half adder circuit. A gets negated to become a 1, and that means the negation of A and B is a 0. Down here we have the negation of B and A. Since B becomes a 1 but A stays a 0, the output of that is 0, and that feeds an OR gate whose output will be 0. The S value in this half adder circuit gives you the sum, and so that shows you that this first digit becomes a 0. Now let's go on to the second column where A is a 1 and B is 0. Since A is a 1, it'll get negated to become a 0. And of course that means that our negation of A and B will give an output of 0. But the one below that, B, which is 0, will become negated and become a 1. And that feeds an AND gate with A, which is also a 1. And that output gives a 1. That feeds our OR gate, which gives our S value of 1 this time. And that makes sense because when we add 1 plus 0, we get 1. Now let's go to our third column. We have A equals 0 and B equals 1. When we add these up, A is 0, it gets negated to become a 1. B is 1, and so our first AND gate with the negation of A and B gives an output of 1, and we don't need to look at anything else. That's going to satisfy our OR gate, and our S value will be 1. S stands for sum, and so the sum there is 1. But here's where things get interesting. What if A and B are equal to 1? When A and B are equal to 1, A gets negated and becomes a 0, and so that negation of A, B, AND gate gives an output of 0. Below that, we have B getting inverted. It becomes a 0, which means its AND gate is going to produce a 0. And therefore, our sum, our OR gate at the end, will give an output of 0. And that's good news. That's what we want. But you know from our work with binary addition that we should have a carry digit here. 1 plus 1 is 2, but we write a 0 and we carry a 1 over to the next spot. Well, look at down at the bottom. The C value is our carry digit. And that's a simple A and B gate. And since those are both 1s, the C value is 1, which tells us that we should carry a digit over to the next column. And you can see that this circuit is actually performing binary addition, where it gives an output or a sum digit, which we write down, and a carry digit, which we would carry over to the next column. And that is at the core of how the first digital computers actually computed. And that brings us all the way back to the beginning of our lesson. What's on your screen is what's called a full adder circuit. What we just did a minute ago is called a half adder, and that is to say you gave it an A and B value and it would produce the sum digit and the carry digit. But what do you do with the carry digit? Well, with a little bit of tweaking, you can make that into the full adder circuit that is shown on your screen. You'll notice on the right side we still have a sum and carry output, but this circuit has an input for C, that is to say, was there a 1 in that carry digit? And now you can see how arithmetic is carried out. Each binary digit would get its own full adder circuit where the carry digit output of 1 feeds into the carry digit input of the next. So I'm going to let this play for a little bit and let the video go along, and I'm just going to let you sort of look over what the possible combinations of inputs and outputs are. This is a clever little animation that shows how that works, where ones are always represented by black marbles and zeros are represented by white marbles, and you can see how we get the outputs that we get. So that's your last lesson. Go after this homework. Be sure to let me know if I can help you out. This is some great stuff. You got to admit it. And I don't think I will see you in the next lesson. That's it. So we'll see you soon.